Bismillah ar-Rahman ar-Rahim. We meet again. This is the second video, which will be the second or part 2 of the revision. As we said yesterday, we have covered module number 1, electrostatics, and we covered module number 2, which is the capacitors and dielectric and electric current and simple circuits. And today, inshallah, the focus will be on atomic structure, binding energy, stability and natural radioactivity, and ionization, and of course the radioactive decay or radioactivity. And after that, we'll talk about, of course, module number 4. But let's focus first on module number 3. Okay, so atomic structure. Let's go here, and so this is atomic structure. Let me just make sure that okay, atomic structure. Okay, so in here, a lot of the things that you know, they are very common. You've seen them before. You know, they have the nucleus, and then you have the orbital electrons, and the orbital electrons are defined. Each orbit can take a maximum of 2n squared. So this will call it, or it is called n is equal to 1, this is n is equal to 2, this is n is equal to 3, and the n's are called the principal quantum number. Okay, so that's these are the n's, and in here we talk, first of all, you need to know, x, z, a, you need to know what z represent and what a represent. And also you need to know what isotopes are, and I think that's it for, you know, in terms of the principle or the definition. The first thing we talked about, and somebody asked me about this, is the binding energy. Now remember what the binding energy is. It's the energy needed when we talk about the nucleus. So the nucleus here, I have protons, I have neutrons, protons, neutrons, protons, neutrons, and so forth. So the protons are positive, right? And the neutrons are neutral. So the binding energy, which is defined as delta E, is equal to m or delta m c squared. Okay, this is the binding energy. Now delta m, if you remember, it's called the mass defect. Okay, defect. So the mass defect, basically, it's equal to, as we'll see it in a minute, but before we talk about that, we need to mention stability, which I'll come back to it in a minute. Stability. So nuclear stability. If we have something like this, where I have 3 neutrons and 3 protons, that means the atom is stable and it is not radioactive. However, if the number of neutrons is not equal to the number of protons, then the atom is said to be unstable. The atom is said to be unstable, and then it will be radioactive, and we'll see that in a few minutes. But let's focus on, first of all, the binding energy. Now, definitely you will need to calculate the binding energy. So calculating the binding energy. Tamam? And the best example which we took in class is calculating the binding energy for the helium atom. And now we know the helium atom has 2 protons and 2 neutrons. So this is 2 protons and 2 neutrons. Tamam, that's the helium atom, 2 protons and 2 neutrons, which is zero or no charge, sorry, neutral. Okay, so what is the binding energy? We said the binding energy is equal to delta m, the mass defect, multiplied by c squared. C squared is simply the speed of light squared. So c is equal to 3 times 10 to the power of 8 meter per second, and c squared is the square of that. That's easy, and we know that. All right. So to calculate the binding energy, it really comes down to calculating the mass defect, and the mass defect is calculated as the sum of the individual masses, which is the masses of the protons plus masses of neutrons, right? Neutrons minus this whole thing, the sum, minus the mass of the helium atom. Okay, the helium atom, and this is taken as absolute value. Okay, so taken as an absolute value. So if we go here, let me just 1 second here. Continue work. Why is this not working here? Log out. Oh, okay. So I don't have internet. Sorry, 1 second, guys. Here, I just wanted to show you on Google the, for example, here. I should have prepared these things beforehand, but it's okay. So here, binding energy. Let me just go to my laptop here. Okay, so binding energy for helium. Okay, calculating the binding energy for helium. Calculating the binding energy for helium, and you can do it using images, and you see the binding energy. I think this one will be good. No, this one will probably be okay. I just wanted to see if we can find something that has, yeah, this one here. Okay, so the I don't know if you guys see this or not. Oh, this is a video. Forget it. Okay, so this is you can definitely get that, and I just wanted to get the binding energy. So the binding energy can be calculated as the mass of the protons. In this case, 2 times the mass of the protons plus 2 times the mass of the neutrons, right? Because we have 2 protons and 2 neutrons, we get that from here, right? Minus the helium atom, which is 4.0028 in atomic mass units, right? So in atomic mass units. So you need to know what the mass of the proton is and what the mass of the neutron is in atomic units. In this case, we have 2 mass of the proton. I'm just looking. Oh, I should go here. So 2 times the mass of the proton, which is in atomic units, the mass of the proton is 1.00758, plus 2, the mass of the neutron is 1.00897 minus 4.0028. So that will give me delta M. And of course, this will be in AMU, so whatever this is, in the atomic mass unit. And you need to convert that. You can do one or two things. You either convert to kilogram, and if you convert this to kilogram, then your delta E, or the binding energy, delta E will be equal to this delta M multiplied by 3 times 10 to the power of 8 squared. Okay, so you know how to convert to the binding end, sorry, to the AMU. So convert, if I go here, convert from AMU to kilogram. Okay, so convert from AMU to kilogram. You see it here, where is my laptop? You see that? Converting AMU to kilogram, that's the conversion factor. Okay, 1.66 times 10 to the power minus, okay, so this is the, sorry, converting AMU is, so you can convert AMU to kilograms, and as you can see this, you can, actually there is a calculator, online calculator that you can use, but you need to know that, okay? So in this case, I don't know what the answer is, but you need to do that. You need to do all of these calculations. Okay, so this is the So this is the calculating the binding energy, which is again there will be questions on that. After that, if we go back to my PowerPoint, after that the binding energy, the stability, and natural radioactivity. For natural radioactivity, I gave you some examples. And now, first of all, you have the homework in which you compared the three natural radioactivities, which is alpha, beta, and gamma. You had to compare these. So please make sure you know the comparison between them in terms of all the different things that I listed in the table. So please review that and make sure that you know that, especially the nuclear reaction. So for example, or the nuclear decay. So if I have a parent that is equal to it has some ZA, and then it it goes to an alpha particle, an alpha particle, which is basically 2, 4. That means here my X, or my the daughter D will be Z minus 2 and A minus 4. So these you have to know them, and you have to make sure that you practice them. And as I said, you have some examples in the homework, in the worksheet, which is or in the revision pack. Let me check that over here. So you have in the revision pack, let's see if we can find one or two. Okay, something like this. So these are the questions you should expect. Okay, so let's say in here you have a positron, right? And he wants you to know or he wants you to predict or say what this X is equal to. So we know that this will be 16 here, right? And 30. So 1630, which is this one here, 1630. That's your answer. Okay, because this is plus 1. All right. So plus 1, this means, no, sorry, this is 15. This will be 14. 14 plus 1 is, so 1430, sorry. 1430, so it will be this one here. Okay. So make sure, in order to get this, you really need to make sure your nuclear reaction is balanced. This is something that you need to know, in addition to the properties and characteristics of each. This is a wave, this is a particle, this is a particle. This is very slow, this is intermediate, this moves with the speed of light. This is a wave that does not have a mass, it does not have a charge, and these guys, they have masses and they have charges. Okay, so please make sure that you know all of this stuff. Okay, next we have ionization. Ionization. For ionization, it is not, I don't think there will be, calculation questions, but there could be a question about, what happens to an electron, because what's ionization? Ionization, when an electron leaves its orbit. Okay, so if this electron somehow through a wave or through a particle leaves its orbit, then that leaves a hole, and then there will be some sort of ionization occurring. But you just need to understand what ionization is, and there will not be a lot of questions on this anyways. Okay, let's talk about radioactive decay. This is, again, radioactive decay. This is where you're going to have, again, one big question. So what did we say about radioactive decay? We said radioactive decay is simply when you have N0 radioactive elements. So some radioactive isotope, okay, and this isotope starts with N0. So N0 is the initial number of particles that are found in the isotope. And then over time, so this will be your N, right? Excuse me. Excuse me. N is, which is time in seconds, and this is the number of particles at any point of time. And radioactive decay will simply be something like this, right? And we said this is described by this equation, N, or this expression, N is equal to N0E minus lambda T. Now lambda, we said it's called the decay constant, okay? And t is the time, okay? N0 is this guy here, initial number of particles, and n is the number of particles at any point here, okay? So, and from here we calculated t half, which was equal to ln 0.5 divided by minus lambda. So this t half, and this is again, it's a very important expression, because it tells us if we know lambda, we can get t half. If we know what t half is, we get lambda. And these are properties of isotopes. So each isotope, it will have a designated or a known t half, and also it will have a designated or a known decay constant. And remember what the decay constant is. Decay constant tells us simply it's an indication of how fast the decay is. So this is very high lambda. This is low lambda. So this is decay is very slow. This decay is very high. Okay, that's what lambda is. And lambda, we said it's measured in 1 over time, or 1 over second, or second to the minus 1. Okay, so the typical questions on this. So, and again, the activity is equal to lambda n, and the mean lifetime is equal to activities lambda n is 1 over lambda. So these are the three sort of formula, well, four. These are the four expressions that you need to make sure you understand which each one of them, what is it, what does it, is it used for. Okay, so the most common example that I either give you lambda. Okay, so lambda is the decay constant, so I give you that, and then I ask you to calculate the time. For example, the time needed for the atoms to decay, let's say, to 30% of the initial value. So this means that n goes to 0.3 n0. Okay, so 30% have been decayed. So this is the 0.3. So that means in my expression, this will be n is equal to 0, e minus lambda t. So n0 will be 0.3. n0 is equal to n0 e minus lambda t. So the n0s will cancel, and then I have 0.3 is equal to e minus lambda t. And of course, I'll either give you lambda or t. Either give you lambda and then ask you for the time, or I can give you the time and ask you for the decay constant. In each case, the solution will be, if I take the natural logarithm of both sides, then this will be minus lambda t. Remember that the natural logarithm of anything to the x, e to the x is equal to x. Okay, and from here I can calculate either lambda or t depending on what t wants. So again, please be very careful. There are two questions in the there are two questions or three questions in the notes in the PowerPoint. Make sure you understand these. Make sure you understand the examples that we did in class. And these will be something that you need. And the most important thing here is actually knowing how to do the, use your calculator to find the natural logarithm, or e to the power of this, or e to the power of that. So that's very important. Okay, so next we move to the last, to module number 4, which is the last one, or at least the last one for the midterm. And this includes the physics of X-rays, the X-ray spectrum, and EM waves. As I said, the interactions, let me just go here. So this includes, as I said, the physics of X-rays, the X-ray spectrum, EM waves, and the interactions of the X-rays with the tissue. Now, these are the ones that we're going to focus only on: physics of X-rays, the X-ray spectrum, and EM waves. Let's go to the white paper and start. So let's start with the physics of X-rays. Physics of X-rays. Physics of X-rays. So let's take it step by step. As we did before, we have the generation or production of X-rays. It includes 3 stages. Okay, so stage 1, we call it the E production. and 2 E acceleration. And the here interactions of E with, or E's with the target. Okay? So in here, in terms of the E production, the electron production, we know that we need to understand what thermoionic emission is. Thermoionic emission. So we need to understand what thermoionic emission is, and that's simply, we know that if you heat a filament, a resistor here, which is basically equivalent to power dissipation, then electrons starts to come out, as I said here. Then the acceleration, which is the most important thing, is that we do it through a capacitor. And remember, this will be your negative electrode, and this this is your positive electrode, and this is your negative electrode. So you have your electrons here, right? These are your electrons, right? And we set it in such a way that the electric field is this way, right? Electric field is uniform this way, and the electrons, because they're negatively charged, so they will move opposite to the electric field. So these electrons, E's, will move opposite to the electric field. Okay? So in doing so, they will go from the negative electrode to the positive electrode. So what are the main things that we need to understand here in this section here? So in here, all you need to understand is what is thermoionic emission. You need to understand that. In here, what we need to understand here, if I start with some voltage V, right, and whatever it is, 50 kV or something like this. So if I start with, this is my voltage, which is the voltage across these two guys, right? That's my voltage here, okay? So if that's the voltage, and I know the distance or the gap, I know the gap between these two guys here. So I know my gap here, you know, the gap, we'll call it D. Then from here, I can say V is equal to ED, right? This is the equation that we, or the expression that we found from the electric field and the voltage, or the voltage difference, and the gap between the capacitor plates. So from here, I can find E is simply V over D. And once I find the electric field, then I can say, remember, these are electrons. So these are E's, which has a charge of 1.6 times 10 to the power minus 19 coulombs. And it has a mass of the electron, which is equal to 9.11 times 10 to the power minus 34 kilograms. Okay, so that's the mass of the electron and the charge of the electron. Is it 34 or 31? I guess you need to check that just to make sure that we don't write something not correct. So Google mass of the electron, yeah, 31, sorry, not 34. Okay, 31, minus 31. Okay, so once I found the electric field, then immediately I say the force is equal to Q multiplied by E, which is simply E, this charge here, the charge of the electron, multiplied by the electric field, which I calculated from there. Okay. And once I find that, then I say that the acceleration is equal to F over ME. F is this here, and ME is this charge. So I found my acceleration in some meter per second square. Now, if I tell you that the electron E started from, or we started with V0 is equal to 0. So it's ejected, started from V0 is equal to 0. Then you can find, this is the important thing, the kinetic energy, or the final kinetic energy, was equal to a half mv final square, which is now I can give you this now. Once you get the, because you have D, right? D, you can find V final is equal to V initial squared plus 2A delta X. So this means delta X is D, is my gap here, right? And A is the one I calculated from here. And V initial It could be 0, or it could be I give you some initial speed. Some initial speed. Okay, so some initial speed, and if I give you it ejected with a speed is equal to this much, then that's on. If I say it's released or started this motion from 0, then you can. But in any case, you need to calculate V final. V final, you plug it here. So that you plug it here, and then you find the kinetic energy. This is basically the kinetic energy by which this electron, remember the electron will move opposite to the electric field. So the electron will move this way, right? And the electric field is this way. So the electron will hit here, and then it will find or it will hit the target in here. And this kinetic energy final, which we said is equal to half mv final square. This is your kinetic energy by which the electron will hit the target. Once you calculated that, then what I need you to do now, so first of all, you have to calculate, this will be in joules, right? You have to convert it to EV. And we know that 1 EV is equal to 1.6 times 10 to the power minus 19 joules. So you need to convert it to EV, so it could be kV, it could be here. Then what I will ask you, I will say, okay, if the ionization, energy for lithium, okay, lithium ionization energy, and if it is lithium, it's the ionization energy. It's about 520. What is this here? Yeah, the ionization energy. It's 520 or something like that. So if I say if the ionization energy, ionization is equal to such and such, will the electron be able to cause ionization or not? How do you do that? You calculate the kinetic energy, and then you see if the kinetic energy is equal to or greater than this, then it has the potential to cause ionization. However, if the kinetic energy is less than the ionization energy of lithium or helium or whatever, then it will not cause ionization. So this is something that you also have to do. All right. So now going back to here. So this is the physics of X-rays. Now the next point, or phase 3. So this is phase number 1. Phase number 2. Sorry. Phase number 2. Phase number 3. These electrons coming in, they hit the target, which is the and then they will have two interactions. We said either Bremse-Strahlung or or characteristic X-rays. Okay. Now in Bremse-Strahlung, we have this is my nucleus here. So the electrons will come and will change their direction now. In characteristic X-rays, they will hit one of the orbital, or collide, I should say, collide with one of the electrons, and then they cause a transition, and then X-rays will come. In any case, and you need to understand the difference between Bremse and characteristic X-rays. You need to understand that, or these two interactions. Remember, it's a particle interaction. Okay, so this means the electron with the electron, so the incoming electron with the orbital electron, or the incoming electron with the nucleus. So it's either both of them particle interaction. So now then they will produce for us something called the X-ray spectrum. And let's look at some of these here because this is important. X-ray spectrum. Okay, so X-ray spectrum. Oh, oops, where's my laptop? Okay, so if you look here, there are a lot of them. And actually, let's look at this one here. Okay, this is the one that, okay, let's see if we can get that. Here, I just want here, this one here. Okay, so this is the X-ray spectrum that you can see in your screen. And if you notice that it starts from, not from 0, but it starts from some value here. I think you see my cursor, right? Some value here. And then it increases, and then there is peak number 1, there is peak number 2, and then it reaches maximum. So you need to know what basically in fact, this is something that maybe this is the best kilovolts X-ray generation, theory of operation. I don't know if you can find find the same website, but this is important. Why is it important? Because it shows everything that we need to know. It starts from here, as I said, not zero, and this is simply the effect of filtration. Now, if there was no filtering, then this will be the unfiltered spectrum. This means that we filter this because the energy, the photo energy, or the photons have low energy, and these are not going to be good for us in the diagnostic range. So what we do, we filter them out. And then we have these, and the maximum photon energy, which is 150, is determined, as we said in class, is determined by the input. Now, the X-ray intensity is on the y-axis, and this is the photon energy. This is the Brem's throttling, this one here, and the characteristic X-rays, the K alpha and the K beta. Remember what the K alpha is and the K beta is. K alpha is the where is the K alpha, K beta? Okay, they don't show that here. But the K alpha is that when you go from L to M and from K to L. So they from KLM. So we have KLM. Alpha when you go from here, and beta you go this way. So please make sure you know the difference between K alpha and K beta spectra, and you understand all of these different symbols and different okay. So please make sure you know that. This is important because there will be a question on these things, you know, the K alpha, K beta, the X-ray spectrum, and the all the filtering effect and so forth. And so this you need to know, and this is the unfiltered and so forth. Okay. Last, if we go here, last is the EM waves. Now for the EM waves, so this is the last thing for your midterm, EM waves. Okay. Now again, let's go, since I have the laptop here. If we go here and we say, we have it already there, but let's say EM waves, EM spectrum, electromagnetic spectrum. Okay, this one here is good. Yeah, this one here. Okay, let's see if we can find this on a bigger screen. Okay. Yeah, this one here. I think you see it. Let me just see if I can make it. Yeah. Okay, you see it on the screen here. So you need to understand the order of these, you know, types of different EM waves. So we start from here, from radio waves, EM, FM, and then we go to microwaves, and then we go to infrared, and then we go to visible light, ultraviolet, and X-rays. Right? So a question will be, okay, and from this diagram, which remember this describes the wavelength in meters, these numbers and wavelengths. So if I go back here to the overhead cam scanner, so it says that lambda for X-rays is equal to 1 times 10 to the power of minus 10 meters. Okay. Then I will ask you, for example, to calculate the energy. Energy will be equal to HF, which is equal to HC over lambda, and that will be H, I don't know, then 6.6 times 10 to the power of, I think, minus 34, and C is equal to 3 times 10 to the power of 8, and lambda in this case is 1 times 10 to the power of minus 10 meters, and this number here is actually in joules. So then you need to convert to EV. Again, 1 EV is equal to 1.6 times 10 to the power of minus 19 joules. That's it. So this is all I will ask you about on the X-ray. Now I can pick an example from X-rays. I can pick infrared. I can pick microwaves. I can ask you to compare the energy, for example, between waves, microwaves, or the energy carried by the microwaves and the energy carried by the X-ray waves. Just to get a distinction between, or distinguish between the two. All right. So, so I think this is the sort of an overall review between yesterday and today, and hopefully this will be, you know, sort of highlights, or you know, at least help you as guide. Remember what I said in the first video yesterday. You need to make sure that you do all the PowerPoints. Now you know what to focus on. 2, you need to do your examples, all the examples in the PowerPoints. 3, you need to do the revision pack, which is all of the problems there. And please make sure that you hand in your revision package at the beginning of the exam on tomorrow. And last but not least, of course, is the old midterm. You need to solve that as well. Make sure you understand how to solve that, which I posted. And if there are any other previews that you get from other students, that's okay as well. And also the quizzes. So if you do all of this, rest assured nothing will be outside, nothing will be in the midterm that is outside. Now, in terms of the structure of the midterm, because of the fact that your number is high, and it will be difficult for us to control the, you know, the sort of the multiple choice. You know, some students tend to look here, look there. So I will only ask questions that need answers, need actual answers. So there will be short answers, meaning that either describe or define or something like this. And there will be questions where you have to calculate, you know, 1 step, 2 steps. And there will be long calculations. For example, the, you know, calculated the final kinetic energy of the electron when it goes from the cathode to the anode, and or from one electrode to another, and also the radioactive decay, also the circuits. So there will be 3 long, you know, long questions, maybe 4 or 5 short questions, and that's it. So it will be very, very, again, please make sure that you study, you prepare. And I wish you the best, and I guess I'll see you later at 11 o'clock. Thank you very much.